Today I talk about something called the bottom-up approach. So we grow nanomaterials from on the substrate, right? So you can make nanotubes, nanowires, nanoparticles. Today we are going to talk about something called top-down. You start from top, then you machine it and get the features on the substrate. So this is a top-down approach. So if you talk about so in microfabrication, so also I'll talk about little bit nanoscale fabrication also. So here mostly talk is on micro size, so your features are going to be mostly micrometers. So also I will talk if you want to make something in maybe several, maybe 10 nanometers, something, still we can use this technique. So if you talk about microfabrication, there are two fabrication technologies. One is something called the surface micromachining. You can make structures like this by doing surface. So then also you can do bulk micromachining. You can make something that's much more thick. So these are two techniques typically we use in microsystem fabrication.
Есть два основных типа микросистем, которые можно делать. Surface плоские, то есть когда все элементы находятся в одной плоскости или не сильно выпирают над ней. И bulk — это когда вы получаете какой-то объемный элемент, например, вытравливаете глубокие структуры. Это bulk micromachining. Micromachining подразумевается не то, что вы фрезеруете это все, а скорее какие-то методы травления сухого, мокрого, о которых будет дальше говориться.
So one thing is when you want to do this kind of fabrication, you have to use good clean room capability. Right? So something everybody is familiar with.
Yeah.
So typical surface, first I talk about a little bit of surface micromachining. So this is mostly CMOS, this is complementary metal oxide semiconductor technology. So in this technology, usually we use something called the structural layer and the sacrificial layer. So then typically if you have something on the substrate, we use some kind of something called the sacrificial layer.
Жертвенный слой, который...
So later you can remove it. So then we have active layer. So then we have to do a lot of things like this called deposition, patterning and etching. So we'll talk about all these steps in details. So mostly the sacrificial layer, later we are going to remove it, dissolve. So then at the end you have freestanding this layer. So, but in this technique, mostly they they are very limited to very special materials. So things like, things like this polysilicon, silicon oxide, silicon nitride, this phosphor silica glass. So then also this is phosphorus silica glass, this is boron doped phosphorus silicon glass. So yes. But micromachining, surface micromachining is limited to this material.
Получается, что в этом методе у нас есть слои структурные, которые образуют то, что нам надо. И есть sacrificial слои, это те, которые жертвенные, которые удаляются, например, при травлении, при отмывке, но они служат иногда для защиты, иногда для формирования изображения. И эти методы обычно ограничиваются вот этими материалами на основе кремния, поликремний, кристаллический кремний, оксиды, нитриды. Вот. Не слишком широкий класс материалов, где это применяется. Но, однако, устройств делается очень много этих материалов.
So, but the bulk micromachining system, they also involve these same things: deposition, patterning, etching of the sacrificial ASM. Oh, you need to have all these steps, right? I'll discuss all these things in details. You have to do deposition, deposit, then you have to etch, then you have to do the pattern, then you have to be for the etching, so then release, all these. Then after that you have to do something called the packaging. So we'll talk each step very.
Pattern is making a mask, yeah?
No, once you make the mask, you have to put it. Yeah, just use the mask to make
the same structure in the.
Yeah, so this is use the mask to make the pattern. Yeah, you're right. First we need to have the mask here. So, but in this micromachining, important thing is they involve a lot of this dry and wet etching for large substrates. So big substrate and thick substrate. So mostly this etching has, we'll talk about all these things, wet etching. So this is more like chemical. Then you can use the dry etching, mostly used in the plasma. We'll talk about all these things. But important thing is, so these structures include very high aspect ratio of fluidic channels. So then you have to have all these components micromachining, including membranes, the piezo resistors, cantilevers. They are like very bulky things. So they all requires all this micro machining. So this involves much more steps compared to surface micro machining.
They are much higher than a surface.
Yes, yeah, you are thick. That's why you have to do etching, what's called the reactive ion etching, or even deep reactive ion. So yeah, this you have to do a lot of etching to make the.
Хорошо. Получается, в объемном микромашининге мы помимо тех этапов обычных нанесения, формирования паттернов и травления еще должны иметь возможность для глубокого травления. Это или химическое влажное травление, wet etching, или сухое травление в плазме, dry etching. И об этом мы тоже поговорим чуть подробнее.
So I will talk about each step very detailed, so don't worry about that if you don't understand. You can see how, if the wafer is thick, you can see each plane, right? 1, 1, 1, or this, the family of 1, 1, 1 plane. So, but these are thick material. Okay, so when we talk about surface micromachining, we use sacrificial layer, mostly we are using silicon dioxide. That's your sacrificial layer. Then structural layer can be polysilicon, polycrystalline silicon. Insulators also can be silicon dioxide or even silicon nitride. So then if you want to put a coating, you can have some, we call the self-assembled monolayer. This, like, you can attach your whatever the molecule onto this substrate. So this is called the surface assembled monolayer. So this involves most of the steps in
the coating is
coating can be even some metal layer. But mostly here we are talking about if you want to attach some
it's functional layer.
Functional layers, yes, exactly. Okay, I'll go through quickly. So then let's start each step one by one. So, So when you first do, what do you do? First we need to get a crystal wafer, right? That's where we start. We start with silicon wafer. So then you have to grow silicon dioxide layer. We'll talk about all these things. Then we do the patterning. So that's the pattern. Pattern means if you have some whatever the shape you need. So that's the patterning. We can use photolithography. So that's mostly using light, right? Yeah, photo using light. Or you can use E-beam lithography using electrons. So here your sizes are small. You can go from UV to maybe red light. But here we are talking about de Broglie wavelength, right? Lambda is H over P. So this can be few nanometers. So this can be nanometer scale. So that's why. So first we talk about photolithography for large scale. So then we talk about this wet and dry etching, then deposit films. So then when you use the clean room with the wafer, you don't make one pattern, because that's a waste, right? You have to make hundreds of the same pattern. So if you have some on the wafer, so this is your feature, right? Whatever, you have a nice thing. So you have to make several of these things. Otherwise it's a waste. So then you can just start, we call the dicing, then you have each one is a one device, right? So that's what this repeat pattern means. So then after you dissolve it, so then you put it in your chip carrier, like you know in your computer chip. So once you have this one, you just put it in all this. So then you can wire bond it and make a device, right? That's what you have in your computer chip, right? So that's the packaging. So we'll talk about each step here.
And we also prefer wire fibers.
Oh yeah. Right. Not the electrical wires, right? Okay, so here is some standard sample when you start. This is your silicon substrate, this one. Then you have silicon dioxide here. This is silicon dioxide. Or even this is this one, SiO2. This one here. Then you can put insulator, right? Insulator, you can. This is sacrificial layer. So this is your substrate. So then you can put the insulator. So this can be the silicon nitride, or it can be even this one, that's also insulator. So then you just pattern it. So you can put a pattern. If you want to continue, again, you can put another sacrificial layer and put another, this is the functional layer, polycrystalline, then another sacrificial layer, and you can beat any time you need. So at the end you can etch it and release it. So then you can make some structures like these things. So we will get into details like this. This is some example.
What's that summit?
That is the company.
Company. It's, and what is it?
This is, they call the micro gear. So this is coming from this poly silicon multi-layers.
It really works, rotates?
Yeah. But you have to have some electrical stimulus. So this is just an example, so don't worry about this one. Yeah. Okay, so this is how, let's start how you do this one. So first, everybody familiar with silicon ingot, you do by crystal growth. So then you have to slice the wafers. You can buy this sliced wafer, right?
Yeah.
You don't buy this one. You can just buy the silicon wafer. Then even polished silicon wafer you can get. So I don't know, students are familiar with this arc here. This will tell you the direction, crystallographic direction, whether it is, whether you have 1, 0, 0 or 1, 1, 0 or 1, 1, 1. So that will tell you the direction of that. So you have to have one surface nicely polished. You can buy already polished surface, you don't have to do the polishing there.
Ребят, получается, что мы выращиваем монокристаллическую булю, она может быть такой, а может быть и сантиметров 40 в диаметре, да, сейчас, самые большие.
Я больше 30 не слышал. Может,
вот. Потом мы ее режем.
Yeah. So this is the chunks that ingot, the crystal growth starting from the seed, right? You just grow this Polish scientist.
Потом мы ее режем и полируем в конце, чтобы получить вейфер, с которого уже можно стартовать весь тот процесс, о котором мы раньше сказали. What about the price for a silicon, for example?
Silicon wafers are very cheap. Like you can get the, if it is undoped silicon, so yeah, we call the intrinsic silicon, we can get one wafer is maybe less than $10, like 6 inch wafer.
6 inch?
Yeah, big one.
6-дюймовый вейфер меньше $10.
What is the maximum diameter of?
So right now, the typical one is 4 inch, but now they make 6 inch one. That's the biggest one you can buy. In the past, mostly.
30, по-моему, больше.
So in the past, it's about this size, 4 inch one. Now you can get 6 inch wafer.
I have seen some pictures with very huge ingots, like this, for example.
Oh yeah, but usually they don't sell those things, yeah. So in standard places, if you want to order, they are either 4 inch or 6 inch standard one. So they are only like less than $10. But if you want to get like N-type, silicon or P silicon, so they are a little more expensive. Especially if you want to put like N++, like highly doped or P++, they are much more expensive. Otherwise, silicon wafers are very cheap. So, but you have to define how much silicon dioxide you want. You can specify if you want, like, say, 500 nanometer silicon, then it's a little expensive. But we usually buy only the silicon wafer. We do oxidation in our clean room.
You do oxidation?
Yes, yeah.
And you have this?
Yes, we can control that thickness, yeah. We only buy the just silicon without oxide. So here is the thermal, how to grow oxide. So if you have this one, silicon, how do you grow this one? So only thing you have to do is react with oxygen. So if you do react at high temperature, you pass oxygen and heat it, you can get silicon dioxide. But that growth is very slow. You can see this, if you want to grow this much thickness, so you can see this is 900, 1000, this slope is less steep, right? So if you want to grow faster, then you have to use water. You just do silicon with water. So then it grows much faster. Still, if you grow silicon dioxide, you can see now growth rate is much faster. This is called the wet oxidation. This is called the dry oxidation. So usually, if you do this way, you can do it faster.
And it is growing up or deep?
So typically we just only talk about the one on the polished surface. So typically you keep the wafer vertically like that. So it's stacked like this. So it grows from both ends, but we only care about from the polish end.
No, I'm talking about how it grows on the surface of the wafer.
Oh,
It's growing to the deep way.
No, on the surface. So you have silicon here, so then oxygen comes here, they react with this one, then this part is mostly
And the thickness
increases, yes, with the time.
Получается, что слои действительно растут. Можно было подумать, что идет реакция, и толщина пластины не меняется, а нарастает как бы внутрь слоя. Нет, на самом деле они растут вверх, толщина слоя увеличивается.
So you can see when the time, so if you go to 1 hour.
And what is the source of silicon for growing the layer? The source
of is just oxygen gas.
Oxygen
gas, yeah. Or if you want, you can have steam, just water, and at high temperature. Here is the
silicon.
Here, this is how you do it.
Гамини, and what about the silicon source?
What's that?
Silicon source. From a gas?
No, we don't have any silicon because silicon is your wafer. So this is your silicon wafer.
I understand.
So yeah.
The thickness is increasing.
Yeah.
And we need to have some silicon atoms and oxygen to grow the layer.
Yeah. So we can no, in this case it's just the diffusion. Growth of film is because this at high temperature.
So diffusion is good.
It is going in, yes, yeah. So this is 800 and like 1000 Celsius. So this is all oxygen because it's all oxygen atmosphere. Temperature is about 1000 Celsius. Then the growth of the film is by diffusion of oxygen into the substrate. It's no silicon gas or anything, only oxygen. So here you have silicon wafer just sitting like this, several wafers. Just pass the gas.
Defect of growth. But in this case, it must be more than enough defects inside the wafer.
More defects?
Defects, yes, because it's the diffusion process is coming. Some of them goes from the middle of wafer to the surface, and
you have some silicon vacancies and the oxygen vacancy. You always have that one, yes. But in the bulk, it's no defects. It's mostly at the close to the surface. You can have some defects, yes. Yeah. So here is the. So this is the wafers. You pass water or oxygen, then just heat it to high temperature. So then also you have to just close it. You need to have a little high pressure also, right? Yeah, because we need to have some equilibrium.
Yeah. And it's okay for mass production. Yes, yes.
Oh yeah, yeah. So typically, your furnace is about this big. So it's in a tube. So tube is about 6-inch quartz tube. So or sometimes it's a malai tube. So inside the tube we have the. So this is the tube. So all this. We usually put about 10 wafers at a time.
And how you control the temperature field inside the camera?
Oh, that's we have the furnace has a temperature controller, so they have PID controller, so you can keep the temperature quite stable. So this furnace is already temperature controlled. You can set to, if you have this one, you have the set point, right? So you can set to like 1000 or 900 C. So you have to wait until you come to the stable temperature. So once it is stable, then we introduce the oxygen.
And
First-
what happens with the and how the end affects seen in such situation? You see, the different wafers stay in different position.
Oh.
One on the beginning, others in the middle. So it will
No,
be-
it doesn't affect too much because your temperature, this is your furnace, so your temperature profile is like this.
okay,
So
understand.
here, everywhere temperature is constant. Yeah. This is very important to have a constant temperature. Yeah.
I see.
Yeah, you are right. Otherwise, they have different properties. Right? Yeah. Okay, so I think this is not very important. So then, if you want to use the evaporation, metal evaporation, so I think everybody is familiar with the, if you want to evaporate some metal, so say gold, or mostly we use, if you want to make electrical connections, we have to use either gold, sometimes we use for aluminum also, so sometimes even platinum we have to use, sometimes we have to use the chromium and so if the gold doesn't stick, so then first we have to put some chromium layer, then put the gold. So
Yeah, yeah. We use this cover.
yeah, okay, yes, chrome and gold. So it's all involves metal deposition. So metal deposition is basically using some very high vacuum system, and you just, if students are not familiar, you just evaporate metal. So metal evaporation can be done by resistive heating. So you can heat by passing a current. So that you have, but it has to be in a very high vacuum. So this is where you need to deposit your material. So this is, we call the UHV, ultra high vacuum. So we are talking about less than 10 to the power minus 8 torr kind of pressure, very low pressure. Right? So then you have your metal here. It can be in a boat. So then you can heat it with some current. You have I squared R,
Yeah.
or you can heat with electron beam, right? So this is a picture of electron beam. Whatever you do is you just melt it and evaporate it. So then this under high vacuum, they will deposit here, right? So that's student should get.
Штамп у вас есть сейчас?
Есть.
Работает?
Да, нет. Магнитронная.
Oh, you do the sparkling.
Yeah.
Yeah.
Надо его принести.
So also we have another one called the magnetron sputtering. So that we have to have a plasma. So I will talk about that one also.
We have this equipment.
Yeah,
That's a
that's a
temperature.
Thermal evaporator.
Yeah, thermal
Yeah.
evaporator.
Yeah.
And Calix have magnetron sputtering.
Magnetron sputtering, yes. Yeah. So these are typically, you can use a thermal evaporator or you can use the E-beam evaporator. E-beam evaporator is, I think it's easier. It's a little more expensive, but easy to control compared to the thermal evaporator. But I like thermal evaporator. That's easy and So that's how we do the operation. So this is the sputtering. Another way to do is, if you have your material here, so target, yeah. So this is your wafer. You apply very high, like radio frequency, or you can even use DC if it is a metal, right? So then you have gas. Typically we use argon gas. So then we start the plasma. So everybody familiar with the plasma? Plasma, typically they have neutral atom, they have ionized atom, and they have radicals. So these ions, they are pretty fast moving. So they just come and knock material from the your target, and they will deposit on the because we have some magnetron, so that you can deposit this one. That's another way to do this one. Thermal evaporator or E-beam evaporator, or third one is the sputtering. So I think they have a sputtering system. And,
Okay, guys,
yes.
some words for a student.
Yeah.
Ребята, вот у нас на кафедре стоит вот такая установка. Вакуум, пропускается большущий ток, раскаляется, начинает кипеть и испаряться образец, и он наносится на, ну, например, мы на стеклышко наносили алюминий, все это прекрасно работает, зеркало сделали. То есть это вот есть прямо у нас, прямо здесь можно попробовать запустить. А плазма, он тоже есть для электронного микроскопа, для маленьких образцов, и у вас тоже для атомного самого. Точно так же создается плазма, она атомы мишени, получается, бомбардируют, они начинают лететь во все стороны. И в том числе на то место, на вейфер, которое вы хотите покрыть этим материалом. Вот. То есть это все есть у нас, можно попробовать, и, как видите, вейферы недорогие, так что welcome, do it in Russia.
Я не использую. У нас, по-моему, что-то я видел на баллоне, по-моему, стоял.
So typically we use like argon, like inert gas. So they just remove material. Okay. So then we call something called a casting. So this is typically we do like if you want to make a like polymer film. So we are going to talk about this photoresist, right? To do that one, we have this polymer. We just take it into a syringe. Then you just put it on your wafer. Then to make it more uniform, you just spin it. We call the spin coater. So when you put it here, they are like this. But if you spin it fast, it spin too fast. So then it will be very uniformly spread. So this is before spinning. This is I have a picture of the spin coater. So that's very easy thing to make. Spin coat is just simply put a simple motor and just put your wafer and have some vacuum to hold it, vacuum jar.
We used fun for computer.
Oh yeah, that's what it is. Yeah. Otherwise, they can be very expensive. Yeah. You can make it for like $2 spin coater.
Это речь идет о том, как наносить фоторезист, который у вас потом будет участвовать в реакциях. Самое простое — шприц, вертушка, и он растекается из середины по краям, образуется очень тонкий и, главное, слой с постоянной толщиной. Потом с ним можно работать. В зависимости от числа оборотов будет варьироваться толщина слоя. Очень простая система.
So I'll show you all these.
А лично куда?
Лишний просто
От числа или от скорости?
от числа оборотов в минуту.
It's okay. So basic idea of lithography is you have to do patterning of many layers, right? If you have your initial sample, then you have to have your, sometimes have insulating material, then you have to put your metal on that one, so it's more like a patterning of different materials. That's what I'm going to talk about in the next one. So here is a very simple example. If you want to make some pattern like this one, suppose on your silicon substrate, I need to make some thing kind of protruding upward in this kind of shape. So this is micrometer scale. So if you want to do it in millimeter scale, you can do by lathe machine, right? You can do it. That's also top-down approach. But if you want to do it in micrometer scale, you cannot do by milling or lathe. So then you have to use photolithography. So what do? If you want to do that one, first you have to do is make a mask of that one. You can do, usually people don't make masks now. There are a lot of companies, you can send you a pattern, they will make it for you. So they are also not very expensive. So you can do masking in your clean room, but it's much easier. We never make masks, so we just, there are companies, in 2 days they send you the mask. So when you get the mask, always that mask, you need to have something called these alignment marks. That's very important, because once you make some pattern on this one, right? So now, when you have to put the next pattern, you have to really align that one. So if you are not aligned, you don't know where you are going to do things. So for that, you need to have some alignment marks. So then you can align everything to that alignment mark. So in the mask, you need to have, so this is the mask. So this is that alignment mark here. So then what you do, you take your silicon substrate, you grow your silicon dioxide, that we already did, right? Then what you do is, we have something called this photoresist. So then on silicon dioxide, how do you do this one? You can do the spin coating, right? By spin coating, you can do your photoresist. Now you take this mask and put it here. You just put it here. That has that pattern, right? You just expose to. So in this case, photolithography, we just expose to light. So if you use UV light, so then this part is exposed to that light, right? So not this part. Only this is the hole here. So if you so if I put this one, so first you have silicon dioxide. Now I put the photoresist, right? This is your, so PMMA or something, say something. Then I have this hole here.
It's a window, yeah?
Yes, yeah. Suppose this is my window. So that window can be this one, this shape, right? So because you have this one already created. So this one, if I draw this one, that window can be like this. So now, when you put here, this is that opening here. When you expose to light, only this part gets exposed, right? Because this is closed. This is all closed, only this part gets exposed. So then this polymer has some special property. When you expose to light, the polymer becomes, we call this cross-linking. So then you can remove that part, or there's two kinds of polymers. There's something called positive or negative photoresist. Positive means the one get exposed can be easily removed by developing. Negative means the one not gets exposed can be removed easily. So So that way you can do whatever the patterning you want, right? So in this case, actually, see now you expose this one here. So this is the exposed part, right? This was exposed here, but this was not exposed. So this is a negative photoresist. So now if I put this one in a solution called the developer, it removes only the photoresist that was not exposed here. Is that clear? So now you have, when I do this one, so only this part gets exposed. Right? So now if I put this in a developer, we call the developer, so then only the one, then you remove the mask. So when you remove your mask, this part is already exposed, so only this part gets removed. Right? So this one, this is the negative photoresist in this example. So this is called the developing. Is that clear?
Yes.
So, for students,
Там может быть позитивное изображение, может быть негативное.
I will have an example for positive photoresist also.
Фоторезист и какой там процесс смывки.
Давайте
Yeah, please explain.
Так, смотрите, процесс. У нас есть подложка, мы на нее нанесли оксид кремния, потом нанесли фоторезист, вот этим вот спин-коатином. Потом у нас есть маска. Маска, это что такое? Это стекло, на нем рисунок. Рисунок или пропускает свет, или не пропускает. Который пропускает, это window, окошечко. Мы маску приложили, it's a contact. Просто вот положили на наш образец. Сверху засветили ультрафиолетовой лампой. Та часть, которая была освещена, то есть то, что прошло через окошечки, оно прореагировало в этом фоторезисте, связи разорвались, его теперь легко смыть. Что получается? Маску убрали, смыли это все. То, что засветилось, в данном случае осталось.
А там и оба варианта есть?
Оба варианта работают, да. Вот. Если позитивный фоторезист, он смывается после того, как его осветили. Если негативный, смывается все остальное, он остается. А потом это все засунули в травитель, и у нас вытравилось то, что не защищено фоторезистом. И мы получили вот такой профиль, как на картинке. Вот.
So after this one, so this is after developing this one, then we do the etching. So etch means, because this is a sacrificial layer, SiO2, you can etch this part, because only this part is protected, right? So only this part gets etched out here. After etching, you get like this. So now you can remove the sacrificial layer, sorry, the polymer here. So then you have this pattern here, right? So that's what you have. That's a very basic way of doing that. So, but this example is for negative photoresist. So I'll show you for the positive photoresist. So there are these steps. First oxidation, then you deposit your polymer, then mask, then expose, then first you develop, so then you etch, then finally remove the top polymer. So then you have the mask. This is very simple, so once you start, it's only like that you can do it here. Is that clear for everybody?
Ребят, про вот эти вот еще марки для выравнивания. Понятно? Если у нас многослойная система, много масок, мы должны иметь специальные метки, с помощью которых мы совмещаем маски друг с другом, чтобы рисунки друг на друга накладывались точно. Если мы ошиблись, у нас все пойдет наперекосяк.
I have a nice video. I think that will help him to. Yeah, let me show you this video. Then I think it's easy to before we do. Okay, here is each step is shown here. So here's the ingot. So here is the oxidation of wafers. These are real pictures. So then this is the spin coater. So here you have wafer. You put your polymer here. Then you spin. Then it's spread here. So then this is the mask. So this you can order the company to make the mask for you. So then you put this, but there's something called the mask aligner. Probably you have that one, because that's basically a good microscope, and you can see in the mask. Yes. So you just put the mask aligner under the mask aligner. You can put this one. So then just expose. So this is positive photoresist. You can see. So if this is your mask. If I put here, then if I expose only, this part gets removed. So that is a positive photoresist. So when you release, you can make this kind of structures. That's a standard. So let me show you this picture. So yeah, after that one, you can etch it through the sample. So then you get this kind of. So let me quickly show the video. Then you can understand this one. So then we can come back here. So you need to make this example. So we are using two masks here to make two different patterns. So let's do this one, then you will understand. So first what we do is, this is my one mask that I can ask somebody to produce for me. This is the other mask. I need to make these two patterns on one wafer. So how do you do that? So this mask has only this hole, this mask has this kind of a pattern already. They make it for two masks. So first thing you do is, let's do one step by step. You just take your bare silicon here. So then you grow silicon dioxide. So this is only like 5,000 angstrom of that's 500 nanometer.
Half of 1 micrometer.
Yes, you have micrometer oxide here. So now what you have is, I have a silicon, then I grew SiO2. This one. Right now, I put my photoresist. Right. So this is now already I put my photoresist. So that's what this looks like. Then what do we do? We just put my mask on that one, right? On this one. So here, take the coated wafer and put the mask on that one. So now I have to expose to light. So now if I'm exposed to UV light, then you remove the mask. So then what we have to do? After this one I have to develop it, right? Yeah. So this has, so then when I develop, so only this is a positive photoresist.
Positive.
This, yes, so only this part is left. So then open and now be exposed to. So then we can put in the etchant, so that will etch through that part, because this is, oh sorry, that's bad. Yeah. This part is protected, right, by the polymer, so the sacrificial layer is protected. So then when I etch this one, so we use wet etch. That means you put it in some chemical.
Yeah.
So
some liquid.
Liquid, yes. So then, so etching, that is something called this BOE, buffered oxide etch. So now you have to remove that residual, the polymer. So remove the resist after etch. Now you can see you have the pattern is already done for the first step. Now you have to put the second pattern.
Yes.
So how do you do that? Then again you have to put your that we do with aluminum. So this one already etched, so we just deposit aluminum on that one. So that second pattern is with aluminum. So we'll go back again, then they can understand better. So then you put the, again put the resist, then put the second mask on that one. So this one, so you can see the second pattern. So that's why we need the mask aligner. You have to make sure they are nicely patterned, right? If you don't have the mask aligner, this you cannot put this one right at the center. So that you have to. So then again you have to expose to light, develop, etch the vapor, and we call the stripping of the resist. Yeah.
How are you doing
Align.
How are you doing?
You have to have the alignment mark. So I'll show you how to do that one. So if you have some alignment mark, then you have to adjust that one to exactly, if that is something like that, you have to make it, turn it to match the two together. So then you will
Mask
Yeah.
or target?
what's that?
What are you changing position? Mask or target?
Usually the wafer. Yeah.
Ага. То есть там не знаю, вот самое.
Yeah. So here is one example of here's the alignment marks, how that works. Oh, this is the two things I think they want to understand the positive and negative photoresist. I just put in one case. So this is positive photoresist. That means if you expose this part, you can etch. Negative photoresist means you only that part stays there, right? So you can see that one. So this is what I want to see, the alignment. So these are the alignment marks. So if you after first deposition, this is you already pattern with this one. So you have that pattern on this one. With the second, you have something on the mask. Then when you put it there, like I said, they are not like exactly, they don't coincide like that, right? Then like you said, either wafer or mask you can turn to make it exactly like this. So if you do this one, that you can see on the computer screen. So then you,
Or a
microscope, yeah. So then once you do this one, now you know they are nicely aligned. Then you can do whatever the next step. Is that clear for everybody, the mask alignment? So I have some even more details how. So another one how to, this is for the, so perfect alignment should be something like this. This is, if you use two masks, right? On the first mask you have the alignment mark, this is on the wafer. So this is the feature on the, so your second mask. So then just align the two. This is once you get used to it, it's pretty straightforward. But the important thing is, you don't make this one feature on only one device. You have to do this several times. That's why the resist always, once you develop an edge, only that parts get stripped. So, but the rest of the resist still good, right? So then you can move your wafer to different position and repeat that one. So that means in one shot you can make about maybe 50 devices in one. So but this also the exposure also you have to be very careful. This is what you need to have, very sharp edges. If you are doing like this or this, they are not good. This can be due to overexposure, this can be due to underexposure. You should aim for very sharp features. So that depends on how long and how dose you are using for the exposure. Okay, so I had some more. what really happens with the resin. So this is a chemistry. So how this cross polymerization happens. So your chains become longer or shorter. So basically what happens is, this is, if you look at molecular weight, originally if that has this much molecular weight, so then after exposure, it becomes less, right? So that's why it's like cross polymerization.
In some connections, chemical connections,
Yes. That's exactly the cross polymerization means. Yeah. Okay, so now this everything we talked about is this etching also. Like I said, there are two kind of etching, right? One is the wet etching, other one is the dry etching. Wet etching is all chemicals. So we use the buffer oxide etchant. So dry etching, mostly we use what's called the reactive ion etching. Or we can use even like xenon kind of gas, and we can do something deep reactive ion etching. So that's, if you want to etch deep into the substrate, then you have to use DRI. So then also this etching can be, sometimes it's anisotropic or can be isotropic. Anisotropic is you need to have something kind of a uniform etching like this, not anisotropic like that. Then you need to have, typically we call this is the undercut, and this depth should be pretty much similar size. So these are some tricks here. Once you get used to it, you can. So this is the dry etching, typically put in a plasma and use whatever the gas you can use, xenon gas or other gas. Same RF plasma system.
Some words for students.
Yeah.
Ребят, речь идет про отравление, да, то есть жидкостное, оно химическое, как правило, изотропное, или жидкостное, или в плазме, как мы уже говорили, и оно бывает анизотропным, когда у вас вытравливаются определенные атомные плоскости, а другие при этом не травятся. Или изотропным, когда все во все стороны травится равномерно. И те, и другие методы.
Here's a nice example of anisotropic versus isotropic. You can see this is the undercut, this is the edge tape. So they should be kind of, so it's not like coming straight like that. So. Okay, then finally, maybe I will talk about, so these features we were talking about in photolithography. They are micrometers, right? Can be 2 micrometer or even less than that. So, but if you want to use nanometer scale, so instead of using the light, we can use electrons, right? Electrons, it's like I said, they have the de Broglie wavelength, they are in nanometer scale. You can use much finer features.
Литография ограничивается дифракционным пределом для света. То есть это сотня.
So you can make much finer features like this. Mostly I use e-beam lithography mostly to make electrical contacts. So this is actually one of from one of my samples. So we usually use photolithography to make these large patterns. So we have mask to make these big pads here. These are by photolithography. But if you want to make much smaller sizes, then we have to use electron beam. So exactly same thing, but when you do the e-beam lithography, usually you don't really need the mask. You have to make some kind of guesswork. So for example, I did a lot of work on carbon nanotubes. So carbon nanotubes are only diameter is only 1 nanometer. Like it is very hard to even see under microscope. I don't know, are you familiar with electron microscopy? Like scanning electron microscope and transmission electron microscope. So with the scanning electron microscope, if it's a good microscope, you can see 1 nanometer sample easily. Yeah. But typically it is a limit. Yeah. If it is not good, you cannot see this one very clearly. So then what we do is, first we make these large patterns like, say, this we can do by photolithography, right? So something like this. This we can do by lithography. The only thing you need is what? Mask, right? You can ask somebody to make a mask for you. Then you just, same way, put your polymer layer, the photoresist, and put the mask, and do the developing, etching, and then deposit gold and release. Then you can get these gold pads here.
It was an electrodes for measurements.
Yeah, these are for the measurements. Yeah. Then we take that substrate and grow carbon nanotubes. So then what you have is something like this, or maybe something here, or maybe something here. So now I want to make connection to two of these leads, right? For that you have to do the E-beam lithography. What we do is, since still we have this alignment marks here, right? So then we have some idea about this nanotube location. So now we put the photoresist, then using the E-beam lithography is done by using a scanning electron microscope. That's the electron source. You can raster your beam, and at the same time you can view the, you can do the imaging, and also you can do the
you can view and draw
at the same time, yes, writing and viewing both. So then, when you put the photoresist, you cannot see the nanotubes, right? So, but you have some idea. Because of that, you can write something along this one, or maybe suppose this person. Then write something from here. It's like this one. So, if I have my nanotube here. If I have my nanotube here, I can just write something connecting this one or something connecting to this one. So then you can do the same thing, you just develop and edge, you can make contact to this one.
Oh, and you write a little electrodes
and
can measure the properties.
Yes.
One.
Yes. So but in one chip like that, we make about 5 devices. I can make 5 carbon nanotube devices. Yes, I had one paper published in Journal Science. We gave about results for about 100 nanotubes. Then the still reviewer said it's not enough. You need to have at least 500 sample data. So we did about close to 500 devices.
Ребят, получается, вот эти большие электроды можно сделать с помощью фотолитографии, но профессор Суманасекера говорит, что единичные нанотрубки можно сюда поместить и с помощью электронного микроскопа, во-первых, их видеть, а во-вторых, нарисовать к ним еще дорожки проводящие. И тогда мы сможем, замыкая, например, вот эти два контакта, измерить свойства проводимости одной нанотрубочки, которая лежит между ними. И так можно сделать для многих нанотрубок и получить статистику и говорить о том, что мы персонально измеряем свойства для одной из них и делаем это надежно. Мне кажется, это очень здорово, когда вы нанометровым объектом единичным можете манипулировать и говорить о том, что вы его померили.
Все-таки надо уточнить, а нанотрубка, это как она возникает? Вот как она возникает нанотрубка, я вот не помню.
Они вырастили?
Как они
How
Как
can
они
we
сделали?
how can we place nanotube in this place?
Oh, no, not, that's why, so nanotubes are everywhere. So maybe, that's why you need to know the position intuitively. So then when you, because this is already nanotubes, then you have a polymer on that one, you cannot see that. So but when you draw the E-beam, you have some idea where it is. So then you just draw the line to connect this one. So that's how this one is done.
Они их везде накидали.
It's a guesswork.
Работали только с теми, которые лежат в нужных местах.
So because we have this fiduciary mark,
Я не понял, как накидали. Как технологически. Вот есть это изображение, есть вот эти электроны. А нанотрубки-то откуда взялись?
How can we put nanotubes to the center?
oh, so that we can easily grow. On the,
Вырастили.
yeah. So that's basically we put the iron particles and put the CVD. CVD growth, yeah.
То есть,
So this is how you do on the substrate. You put iron nanoparticles, then you put methane gas
okay.
at high temperature, then they grow.
Like in yesterday lecture.
Yes, yeah.
Вчера вы тут подробно говорили, что есть частички золота, накидать, они очень хорошо растут.
But we don't need a lot of nanotubes. That's the problem. If you have like this, that's not good. We need to have very individual nanotubes.
Individual.
Yes. So you can see you need to have photolithography and E-beam lithography. And also some people, maybe people like him, they do something called the lithography. What's called the interference, what you call holographic lithography. So the optics people, they have two beams interference. So then you have the interference pattern can have much less than 100 nanometer, right? Interference. So you can use, that's called the holographic.
Like in the lab of Professor Mendes.
Mendes is using, lithography. So still with this you can use ultraviolet, deep ultraviolet, right? So then if you make interference, then your features can be much smaller.
То есть как они исследуют свойства нанотрубок, они с помощью нанотрубок делают электрический контакт. Я правильно понимаю?
Да.
Нет, мне как... Вот я сейчас чуть не помню.
Что-то вот это. То есть электрический контакт, вот как...
Мы сейчас, мне кажется, вообще
Да,
о разном говорим. Could you repeat? So big
Yeah. This is
electrodes we did with photoresist.
Yes.
Потому что здесь мы поняли, что это сделано для того, чтобы сделать микро...
UV photoresist and
и соединить
beam photoresist, right?
Yes.
We didn't measure some properties of nanotubes, right?
Oh, we did, yeah.
Они подключили.
I don't know whether you did, so maybe different project, yeah.
What we expect now?
Это кто вам сказал?
Measure properties of nanotubes or created
Yeah,
tiny electrodes.
To measure the nanotube property, you need to connect two wires, right? That's all you need to do. Suppose,
So now we discuss about creating the small parts, right?
yes, yeah. So,
Роман Сергеевич, мы сейчас обсуждали как
so let me explain. There are two ways to do that one. First, you can make the, say, gold contacts. Like, so this is by photolithography. Okay. Of course.
А тоненькие с помощью beam вот этой фотолитографии.
So
Мы не измеряем никаких свойств нанотрубок здесь.
this is by photolithography. This is where I make the wire bonding, right, for the chip. So I can make so. But there's no connection between these two. One way to do is you just do this one. These are gold contacts. You can do by using the mass like this one. This big leads. So if you have nanotubes in a solution, you just drop cast here, then you expect some wire will break this one. Then you have a device, right? So, but it's when you do that one, it's hard to say whether you have one nanotube. So there can be more. So that's why what we did was, you just grow nanotubes, so that nanotube can be here one, maybe another nanotube here, another nanotube say here. So now, first we do the AFM or something, so then I know location of nanotube. So that, because I have this alignment marks here, I have good idea where the nanotube is. Now, on this one now I have to put my photoresist. So then I have to, no mask here. So I just write E-beam. So when you write E-beam, I can write from here to here. This is the electron beam.
Yeah.
Because this one now is a guesswork, but I know where it should be because of this mark. So then I write another one like this.
This area became.
That is, now after polymer, you just draw this one. It's like exposure now, but exposure by UV, sorry, by E-beam, right? So now you develop it, so then you can.
It then became conductor.
Yes. So then put the gold. So then that is this line. So that is this one here. Like something like small one here. So that is connecting the wire.
The aim was to measure the property.
Electrical properties of one.
One,
Yes. Yeah.
Нет, все правильно. Это получается вот эти подводила электронным лучом, вот это, да?
So if I do this one, so now if I connect.
Он тоже через фотолитографию? Или он сразу туда электронным лучом напылял металл? То есть,
So photolithography is not enough to.
они не могут сделать тоньше, потому что предел функционный, а здесь длина волны меньше, соответственно, может сделать тоньше.
Можно дорисовать.
Да.
Yeah, you can even make nanoparticles like that. You can have.
Ну, в принципе, можно и вот какой-нибудь там микросхемы миниатюрные сделать разборку на это.
Да.
Это метод вот именно для таких наноматериалов.
Да, для очень маленьких мощностей.
E-beam lithography you need to have for nano electronics.
Yeah. Very interesting.
So that's actually it's not easy. Sometimes when you draw this one, you might make this one nice connection. This one probably might go like that. Then that's not good. So if you make.
It's a very tiny technology. Very tiny.
Oh yes. This is still like R&D level. It's not for.
Not for mass
Not yes. Okay. So you can see a lot of these transistors. Here is the. This is not from my. So this is the scanning electron microscope here. So used for the E-beam lithography. So good thing is, yeah, we also have the Joel. I think you use the Joel one, right? Yes. See you. So your beam diameter you can learn. 4 millimeters.
4 нанометра, сколько атомов там?
Несколько десятков.
То есть там ангстрем, да? И где-то 40.
Это 40 ангстрем, это 10 атомов.
10?
10, да.
Это вообще...
But also if you want a smaller separation, there's something called the oblique angle deposition. So if you have something, suppose when you do E-beam like this, you are exposing this area, right? But if you do at an angle like this, then you are only exposing only this part, right? Yeah. So then you can do next one from this side, then you have, so you can reduce that separation.
Okay.
So you can have something called the angle deposition. Yeah. That also we try sometime to make a much narrower separation. We can do this. So you, after this one, you just turn the wafer and deposit this way, then you can make short separation. Yes.
Angle, what about this one? This?
Yeah, so that then you can even, with the angle, you can make, it's more like shadow masking, right? Yeah. Okay, I'll stop here. So,
Thank you. Guys, what about these questions?
Я хотел спросить про коммерциализацию. I want to ask you about the commercialization. Sorry.
what's that?
About the commercialization of this
Polymer?
no, of this technology.
Oh,
Do
okay.
you have some collaboration with industry? Or
Oh, yeah, because
maybe you give you some one or two example how much you can earn with this technology and what.
yeah,
what
actually, one of my PhD students, he's now working with the Intel company. So yeah, so he's mostly working on this area. Or you know, Ruanda?
No.
No.
I can talk about Евгения Моисеева, там работает в нанотехнологическом центре.
Oh, Eugenia, yeah. She's now working in the clean room.
Да, у них там большой центр, и они, вот она нам рассказывала, что они там, у них основной заказчик это Кремниевая долина, вот они такие вот большие вот эти им заказывают микросхемы, и они их туда продают.
Yeah, but the thing is, e-beam lithography, they do a lot of work at Intel. Yeah, but we sometimes Rwanda comes to our campus and use the clean room facility to make some devices because they have much better clean room capability than Intel. But still, they do little bit R&D work, so they collaborate with us. But photolithography, everybody, even like printing technology. So how the printers work with the house, so they use the micro patterning.
Микроподвижку с шагом 10 атомов соединения. Например, 10 атомов, тяжелый шаг микроподвижки.
Да, без проблем. Ежепозиционеры с нанометром спокойно может, да? Если вы вокруг обеспечите тепловые условия, отсутствие вибрации, то сам позиционер.
Там 10 нанометров было про диаметр пучка.
Да, диаметр пучка. Ну, так его надо тоже вести с этой точностью.
То есть у них не стандартный микроскоп, а они выше как-то...
Нет, ну если это пучок, то не фокусируем линзами.
Все вещи, связанные с тепловым расширением, все можно сдвинуть.
Yeah, but when you do this nano size scaling, the cleanness is very important,
Yeah,
right?
it's very important.
Yeah, if your dust particles are sitting in between. So you have kind of a clean room.
Yeah.
Yeah, that's what we also started, small clean room with lot of filters.
One more question from our
Yeah.
Can you tell about the typical methods how to prepare mask? You told that you
Yeah, usually we outsource it.
Yeah.
There are companies,
How do they do it?
So they use the chrome metal. So they also do the same thing. They have, first we need to print.
To print, it's very small.
Yes, yeah. So you have to make a kind of a CAD kind of drawing. So then I think they transfer that pattern to that chrome mask. Yes, yeah. That's a lot of work we can do in our clean room, but it's easier to outsource.
It's a very it's printer, it's device.
Yes, yeah. We only have to send a CAD drawing, AutoCAD, so they do it. Yeah, it's not very expensive, so it's not worth doing in the clean room.
Насколько у них сильно отличаются свойства микроконтактов от свойств вот этих круга? Мерить сопротивление. What is the definition between the properties of microcontacts and properties of nanoparticles?
Oh, so typically nanotubes, interesting thing is mostly we do something called the field effect transistors. So what we have is usually we use our silicon. So mostly we use silicon, highly doped silicon. So then we have silicon dioxide. So now suppose we have carbon nanotubes here, then we have these two gold wires. So that's where we have the, so this is source and drain. So then we use this one as your back gate. So you have first we apply current and voltage here. So this is the we call I source drain current. So then we apply another voltage. So this is the gate voltage. This is we call the bottom gate. So if you want, you can put a top gate. So if you have a nanotube here, you can put some, say, silicon dioxide and put a gold. Then you have the top gate. But this is much easier.
So I understand.
Yeah.
But please say me about the conductivity.
Oh yeah.
In
yeah.
what scale?
Yes, yeah. So carbon nanotubes, important thing is they have two kind of carbon nanotubes. One is semiconductive, one is metallic.
Yes.
So semiconductive we can easily look at if I do the gate voltage, IDS. So they show some if it is P type. So you have so typically these are P type material. So that means you have no. So it's show this kind of behavior because it's on for negative voltage and off for positive voltage. If it is a metallic, they are constant.
I understand.
Yeah. There's no gate dependence, right? Metallic.
Just
Then also carbon nanotube.
Potential contact.
Yeah. If they are close enough, they can show ballistic transport. So you can easily tell whether it's semiconducting or metallic by this gate voltage dependence.
Okay, thank you.
Yeah.
Is it possible to control isotopic etching?
What's that?
Is it possible to control isotopic etching?
Isotropic etching?
Yes.
Yes.
Could we obtain a certain three-dimensional?
Yeah, so
structure?
sometimes you have to do this like etching from underneath. So that's involves a lot of. Sometimes you have to do little bit wedge etching, then followed by some dry etching, use on some like xenon kind of thing. So if you want to have like etching from underneath, so that's you have to do both wet and dry etching. So if it is a thick sample, you have to do that. If it is a surface micromachining, I think one of the etching is enough.